All right. Let's get started. Welcome, everyone. Welcome to another lecture. Um, as I mentioned, I don't remember where I mentioned. Maybe I mentioned in the last video. Maybe I mentioned in an email. But I did mention that I wanted to cover an extra lecture with you guys because with all of the craziness that's been going on, we have missed a few lectures, and I just want to make up one of them. So I decided that this lecture in particular would be the one I would want to make up, which will put us in a good place for the remaining two lectures of the semester. And this lecture is one on vectors. And I figured that most of you would already actually know about vectors, and I need to just remind you, but it's also a topic that is, especially relative to all that we've been doing, is a pretty easy topic to kind of catch up with on your own. So even if you haven't seen it, we won't be talking about anything too crazy compared to all the things that we've been doing before. So if there is going to be an extra lecture that I want to put in where you guys aren't necessarily here, it's asynchronous, this will be the one. And after this, we have two lectures coming up and we'd wrap up the semester there. So with all the craziness going on, we have not and we will not complete all the things I wanted to do when I started this semester, everything I had in mind for the course, but we have covered pretty much everything, all the essential skills that you would need as a Calc 2 student, and you're definitely set up for the next course if you need to go there. In fact, if you are moving on to Calculus 3 or Multi 1 as they call it at Fordham University, you guys actually have a head start. You guys will be ahead of the game, ahead of the curve when you're in Multi 1 with your classmates. You will have seen things already that you're going to learn the next course. So semester didn't go quite as planned, but I don't think this year has been going as planned for anybody. However, at the end of the day, we did kind of did okay here. So didn't go according to plan, but I'm not totally upset about how things went down. That being said, let's not waste too much time. Let's actually jump into the lecture. So here's what I wanted to talk about, vectors. And it's going to be an introduction. We're going to keep it very basic. Vectors are indispensable when it comes to 3 dimensions and higher dimensions, actually. It's just a better way of thinking about location and curves in dimensions higher than 2. Vectors are going to be how you want to think about location for one of many reasons why you'd want to use them. They're actually very, very important, very, very useful. And I just want you to know what they are, how they work, and that will actually help us out a lot with the next 2 lectures and with the future of calculus, because once you're working in 3 dimensions or higher, at some point people are going to talk about vectors. So let's actually just learn the basics, or let me remind you of the basics, because I think a lot of you will actually know about vectors already. That being said, let's jump into it. So a vector is a quantity having both magnitude and direction, and we're right here with the definition. So geometrically, a vector is represented with an directed line segment or an arrow. So you just draw an arrow, and that's called a vector. And normally, the tail of the vector here, that's called the initial point. And the arrowhead, where the arrowhead ends up, this is called the final or terminal point. And the length of the vector, how long this arrow is, also has meaning. That's called the magnitude. So a vector, or a vector quantity, is a quantity that has both magnitude and direction. So there's some notion of what size it is, and there's also a notion of what direction it's pointing into. This is to be contrasted with things that we call scalar quantities. These are things that have only magnitude. So for example, a real number, the number 5, we would call that a scalar quantity. It only has a magnitude. There's only a notion of size. And -7, that's technically a magnitude as well. It only has a notion of size, and there's some notion of it having a negative size, but it's still a size notion. But sometimes you actually want to indicate direction along with the magnitude, and to do that, you would use vectors. And we can represent these graphically as just arrows, directed line segments. Moving on, we can name vectors. Now, there are a couple ways we can name them. We can actually just use a lowercase letter, and we can use a boldface or to write a little arrow over it. Now, normally when someone is writing by hand, they would write the arrow because writing by hand a boldface is kind of weird. Another way to talk about labeling a vector is actually label it based on the points that it travels between. So if we're in 3 space, so remember, we draw the axes like this, okay? And so let's say here there's a point A, and then over here there's a point B, and then I have a vector that's connecting A to B, then that vector might be called AB, right? Where it's understood, you point the arrow from the A going towards the B, it's understood that B represents the final point, A represents the initial point. But we could also just call that little a and put an arrow over it. Once you write an arrow over it, that indicates that we're talking about a vector. So normally A, you would think of this as a scalar if someone writes it, whereas A with an arrow, you'd think of it as a vector quantity. Okay, so there's a couple of ways to name vectors. Let's talk about equality of vectors and position vectors. So basically, a vector is defined based on its magnitude and direction, not necessarily on where it's positioned. So, it's a word line. So we could be, let's say, in the XY plane, and I could have a vector here moving up, and I can see, for example, that, oh, it's moving up in a direction of 45 degrees from the horizontal, and it has a length 2. Then it turns out that any other vector in space that is moving up at 45 degrees and has length 2, they're actually considered the same vector. We do not distinguish between these vectors. Okay, so a vector is totally in terms of its magnitude, defined in terms of its magnitude and direction. A vector can be moved all over space, and as long as it's pointing in the same direction and it has the same length, we consider it the same vector. The positioning of the vector does not matter so much. There's one context in which it does actually matter, and this is when we have what's called a position vector, right? So position vectors are extremely useful, and normally when we do want to talk about locations and curves in space, we are going to use position vectors. So all that a position vector is when we do consider the starting point. So a position vector is just a vector with a starting point at the origin. So I can have my vector over here. That's my vector A, and this is the guy, let's say he's at 45 degrees and he has length 2. Then if I move him so that his initial point starts at the origin specifically, right? And again, 45 degrees and length 2, this guy is called the position vector A. Right? So vector A, it's the same guy moving all around, but when we situate his initial point at the origin, specifically at the origin, we call it a position vector instead. Why do we like to call it a position vector is, well, I should probably show you, I can kind of show you based on this. So it's called a position vector because it can locate position. So if I have the coordinate A1, comma A2 in R2. I defined it a little bit below, but let's just continue. If I have a position vector that starts obviously at 0, 0, and it hits that coordinate A1, A2, then I would call this the vector. Its notation can look like the same coordinate, but with square brackets. So it can actually, where this vector ends up, can actually talk about the position that you want to hit if you start at the origin, where the horizontal distance moved is the A1. So you move A1 to the right. If A1 is positive, you move A1 to the left if A1 was negative. And the distance you move up is A2. And normally you would move up if A2 is positive and move down if A2 is negative. So this does have a positional thing that goes along with it as long as you're starting at the origin, right? So that leads us into this notation here. If you have a position vector whose terminal point is A1, A2, we call it this guy. So we write this notation now. To be fair, in higher mathematics, you kind of always use this coordinate notation. But especially if you're like a Calc 2 or a Calc 3 student and you're just learning about the difference between vectors and actual coordinates, we do recommend that you emphasize this here. And in class, when I want you to know that you're dealing with a vector, I am going to expect that you're writing this notation. So the coordinate is linked with a position vector. And so that's one of the reasons why it's called a position vector, because it actually brings you to a certain position. And in 3 dimensions, 3-dimensional coordinate can be expressed like that, but you can talk about n-dimensional position vectors as well. They're discussed like that. And strictly speaking, a vector that you can label any vector by its position vector notation as well, just so we're clear, because vectors are always the same if their magnitude and direction are the same. Moving down, so I told you what in the R2 and R3, which where we're going to spend most of our time, the first coordinate is going to be called the x component. That corresponds to the x coordinate. And the second coordinate is the y component of the vector, which corresponds to the y coordinate. And if there's a third coordinate, we call that the z component, which corresponds to the z coordinate, etc. So for example, I can write down the vector 1, 2, 3. It would have x component 1, y component 2, z component 3. And I would be able to sketch what that vector would look like. So for example, in 3 space, you can almost plot it the same way you would a coordinate, except you don't just plot the location. There's a whole magnitude and direction. So I would move 1 on the x, find 2 on the y, then rise up to a level of 3 on the z, and that is the location 1, 2, 3. And the vector 1, 2, 3 can be represented by an arrow starting at the origin and moving to hit that point. That would be the vector 1, 2, 3. And that's how you can actually represent them. So you can identify a coordinate, and the vector whose notation is like that coordinate with a square bracket is just the vector that goes from the origin to hit that. But again, you could actually move that, right? You could actually move this to, oh, I didn't want to do that. You could actually move this to be in any position you want, and he'll still be called the vector 1, 2, 3, as long as it points in the same magnitude and direction. Make that seem somewhat similar. Okay. So that's how we could label vectors. Now, there are going to be times when we're going to have, and I mentioned that up here, where we want to think of a vector as connecting 2 points, moving from one point, which is the initial point, to another point, which is the final point. And you might want to think, if for 2 random points, how would you actually figure out what the components of the vector that would go from one point to the other, especially if the one point isn't the origin. Then it turns out you have this final minus initial idea. In other words, to go from a point x1, y1, z1 to a point x2, y2, z2, it's just the final point minus the initial point, in the sense that the x component will be x2 minus x1, y2 minus y1 for the y component, and z2 minus z1 for the z component. So let's actually do a quick example here. So suppose I have a coordinate 4, comma, minus 2, comma, 0. And I have another coordinate. Now, I don't know how these are situated in space. It doesn't matter. This is just for illustration purposes only. If I want a vector that goes from this point to that point, and I want to know, well, what is such a vector? Then I could write that as the final minus initial. So if this is the final point, and this is the initial point, it is going to be all the final numbers minus all the initial numbers. And that will give you the component form, as we call it, of the vector. So the vector A is actually going to be the vector minus 3, comma, 5, comma, 5. And that would be the vector that connects this point to that point. Okay, so you have this final minus initial idea. Now let's talk about some properties of vectors. Another thing I'd want to remind you of, well, if you can think of a position vector in the sense that I just mentioned it, you can think of a position vector as a vector that's connecting the origin to some point, A1, A2, A3, right? So this is the vector A1, comma, A2, comma, A3. Now, you might want to think, well, what is the magnitude of that vector? It turns out then, if we can measure a vector as connecting these 2 points, then the magnitude of the vector is equal to the distance between these points. And we actually have a formula for that, right? So this would be the square root of A1 minus 0 squared plus A2 minus 0 squared plus A3 minus 0 squared. This is the distance formula, and that is what we mentioned here. So if I have a vector, and let's use 3 dimensions for instance, we can define what's its magnitude. And there are 2 different notations here. And it's just going to be the square root of the sum of the squares of the components. Okay, so for the vector above, for example, so if I have my A equals minus 3, 5, 5, then the magnitude of A, which by the way, you can use either notation, so either or. Now, normally I'll just write this one. Some people like to emphasize that they're talking about the magnitude of a vector as opposed to the magnitude of a number by using a double absolute value. It doesn't really matter though, because the arrow is what indicates to you that you're of the magnitude of the vector. No one's going to make a mistake of not knowing, well, which absolute value do you mean here? Absolute value like it's real numbers or magnitude of a vector? It's going to be clear when you're talking about the magnitude of a vector because there's going to be a vector inside of it. There won't be a number inside of it. So yeah, and we can actually follow by the distance formula. By the distance formula, this is just going to be the square root of the first component squared plus the second component squared plus the third component squared. So that's 9 plus 25 plus 25. So the magnitude of this vector, or the length of this vector, is the square root of 59. So if you were to look at the vector A in this situation, its length is the square root of 59. Okay, so that's how we would do that. And hopefully you're following so far. I'm doing a lot of definitions here, and I do know I'm going a little bit quickly here, but everything I'm saying, I do have it typed up. I'm just going through, and I think just me going through and talking here is good enough, because when you're looking at what I'm doing here, compared to like integration or finding a Taylor series or something like that, it's something that we can go a little bit quicker for. So hopefully you're following, but we're just going to keep going at this pace. And anything that you need to go over, you can, I'll post a PDF of the notes and you can go over them. So let's talk about some operations on vectors. Okay, so operations in the sense that when you're talking about numbers, operations just mean, like addition, subtraction, multiplication, division, things that you can do to combine numbers and get a new one. Well, we can also do the similar things with vectors, right? So if I have two vectors, what are some ways that we can bind them and do mathematical operations with them to create new vectors that might have some meaning for us? Well, there are two main operations that I want to talk about. There are addition of vectors, and then there is a scalar multiplication of vectors, right? So these are the two operations. We call them addition and scalar multiplication. These are the two basic mathematical operations that you can do with vectors. And so these are defined component-wise. They're defined pretty naturally, how you would expect. So if I have two vectors, vector A, which has components A1, A2, A3, and I have vector B, which has components B1, B2, B3 in R3, and let C be some real number, it's some scalar as we would call it, then we define the addition of vectors A plus B to be the addition of corresponding components. So it's the vector that you get when you add the corresponding components. So you'd add A1 plus B1, that would give you the X component of the addition. A2 plus B2 would give you the Y component of the addition, and A3 plus B3 would give you the Z component of the addition. Then there's scalar multiplication, which, as the name suggests, it is multiplying by a scalar. And what you would do is you would multiply each individual component by that scalar. So the vector C times A is C times A1, comma C times A2, comma C times A3. And so these are the two operations, how they're defined. And I do want you to note here of how scalar multiplication would behave if your C is And we're back. Actually had some technical difficulties there. Things actually got disconnected. But okay, we're back. Let's pick up where were we talking? Okay, so we're talking about operations of vectors, addition and scalar multiplication. One thing I want you to realize, a few things I want you to realize about scalar multiplication is if you multiply by a constant that is positive, you will point in the same direction as A. And if you multiply by a constant that is negative, you will actually go into the exact opposite direction. You'll go along the same line, but you'll switch. Your initial point and your final point will actually switch locations. If your constant is 0, the scalar is 0, then you obtain something that we call a zero vector. How this guy would look is kind of how you'd expect. He would be a vector where there's just 0, 0, 0. All the components are 0. But he actually has, he's very important, don't get me wrong, but he actually has some strange properties. The zero vector is kind of a vector that does not have a direction and at the same time has all directions. It has undefined direction, to be kind of weird, but it's a very important vector. We'll probably talk more about using that later on. Now, in general, if you want to talk about the magnitude of CA, A is the vector, then it's going to be the magnitude of C times the magnitude of A. And just a naming note on the addition vector. Sometimes this is called the resultant vector, especially in physics context. So if you hear the term resultant vector, they're usually talking about adding two vectors or combining them via the addition operation. Now, geometrically, what does all this mean? Let's talk about what addition and scalar multiplication would mean, because I want you to have a picture in your head of what these things are. So let's say I have a vector A, right? So let's say that's my, do I want that color? No. Let's go to, no? Not giving feedback now. Okay, so let's say I have a vector A, but that looks like this, boom. And I have a vector B that looks like this, boom. Then what would A plus B look like? A plus B would be if I took the vector A, boom, and then from where A ended, I started there and attached the vector B, boom, so this is B. Then the vector that goes from where A started to where B ends, that is called the vector A plus B. So it's like you have A and then you added B onto the end of A, right? So this is A plus B, aka the resultant vector. Okay, which you might hear it called. So yeah, that's what addition would kind of mean. Geometrically, that's what it would mean. You just attach the two vectors together. And I don't know if I want to write this as a, right? So it's the same vector B that we saw from up here. Okay. Now, as indicated above, which I mentioned, negative scalars flip the vector. So, and in general, scalars scale the vector in the sense of the English word of scaling, I think. So if I had a vector A, right, then negative A would literally turn it around, right? So it's running along the same line, almost same direction, except your final and initial point switch. If I were to say 2 times A, then it will scale A. It will maintain the direction, but it will make the length twice of what it was. So if the length here was L, the length here is now 2L. Now, I could have multiplied by -2, and that would just be, again, the magnitude is 2L, but now the direction is exactly the opposite. So here, again, the length is 2L. Okay, so that's what scalar multiplication does. It stretches or shrinks your vector. You could also have, say, like a half A or something like that, right? And this would be 1/2 A, and this is just a vector of half the length. The length here is 1/2 L. Okay, so addition is like you combine two vectors, tail to head, tail to head, tail to head, and then you go from the start of the first one in the addition all the way to the terminal point of the last one in the addition. That vector is the sum of vectors, the addition of the vectors. We can do scalar multiplication. This literally stretches or shrinks a vector. If it's positive, then it will maintain the same direction. The final point will be in the same direction relative to the initial point. And if it's negative, you're multiplied by a negative scalar, they literally turn around. You go along the same direction, along the same line, but you're moving in the opposite, exact opposite direction. Almost, you make a 180 degrees. In light of this, I want to talk about how you can think about vector subtraction, because there is a way to subtract vectors. And how do we think about this is similar to how we would think about it in terms of numbers, actually. To take the vector a minus b, or find what that vector is, it really means to take a plus the negative of b. Kind of like how you'd say, oh, 2 minus 3 is the same as 2 plus negative 3. With vectors, you can do the same thing. So what would that mean? So again, let's say I have my vector here. This is my vector A. And then this is my vector B. Then that would mean that this is the vector negative B, or something similar to that. And so if I take A and add to that negative B, which goes this way, so this is minus B, then the vector that starts here and ends there, that's the vector A minus B. So if I have two vectors like A and then B, this green vector here, that's A plus B. And if I were to take the opposite direction of B, minus B, and add A plus the minus B, that red vector is A minus B. Okay, so geometrically, that's what's happened, and that's like, this is so useful in physics. If you're not already using this, you're probably already using it if any of you are taking physics, but it's very useful in physics to kind of visualize forces and all sorts of things. Now, what I do want you to, another thing I want you to know is the definition of parallel. And parallel kind of means that it's running along the same line. So we call two vectors parallel if they are scalar multiples of each other. So we say A and B are parallel if A is equal to some scalar multiple of B, C a scalar. Or B is some multiple of A a scalar, C a scalar. Right? By this definition, of course, the zero vector is parallel to every other vector, which is why I mean it doesn't really have a particular direction, because I could just take C to be 0 and I would get the zero vector. But that's what it means to be parallel. So all of these things that I mentioned up here, so all of these vectors are all parallel. Example, these are all parallel. Okay, because they're scalar multiples of each other. All right, so that's what it means to be parallel. In terms of some more mathematical properties, we have the following. Vectors will obey these properties. Addition is commutative still, so B plus A is the same as A plus B. The zero vector operates the same way that the zero scalar does when it comes to addition. So if I take a vector plus the zero vector, it doesn't make a difference. And if I take a vector and add its negative, it gives me the zero vector. Addition is still associative. Distributive law still holds for scalars over vectors. So that gives you these two. And of course, the scalar 1 times A is A. That follows straightly from the definition. And of course, multiplication of scalars is associative. So all of these are just properties that we can use when it comes to vectors and calculating them. And this works in any dimension, by the way, so not just in 3 dimensions. However, let's actually do some examples of us working on all of these in 3 dimensions. So suppose I have A vectors A, B, and C, A and B here, like 1, 2, 3. It's too late. A is the vector 1, 2, 3. B is the vector -4, 0, 5. Based on this and everything that I've mentioned before, let's actually compute all of these vectors. Okay, let's jump into it. Now, at this point, I would feel comfortable enough actually asking you guys to actually pause the video and even try these before you even see me doing it. It's the definitions are very natural. So the magnitude, just use the distance formula, the square root of the sum of the squares of the components, and addition, you deal with it very naturally how you think, add corresponding components. Scalar multiplication, multiply all components by the vector. So you can use all those rules and try to do these examples here. So for example, let's just go through and make sure we know how to do all these. So we know that here our A equals 1, 2, 3. Our B equals -4, 0, 5. So what is the magnitude of A? Well, it's going to be the square root of 1 squared plus 2 squared plus 3 squared. And that's going to be square root of, looks to be 14. Voila, that's it. B. What is A plus B? Touch my face. Bad Jhevon. Okay, so if we do A plus B, this is, well, 1, 2, 3 plus -4, 0, 5. Now, the next line, you can write this. I'll write it out just so you can see what I'm doing, but in general, you don't have to write this line. 1 plus -4, 2 plus 0, 3 plus 5. I don't need to write this. I'm writing it just because it's the first time we're doing this whole topic and I want you to see what we're doing. Don't need to write this out. But just know that you're adding corresponding components. So it's the 1 plus the -4 will give you -3, comma, the 2 plus the 0 will give you 2, comma, the 3 plus the 5 will give you 8. And so that's the answer here. That is A plus B. And again, geometrically, this vector is going to behave like this green vector in relation to these two when it comes to that. What about A minus B? So I want to make sure that we're not forgetting them and I'm not scrolling down too far for you to forget them. A minus B. So C, we want to talk about A minus B. Well, that's just going to be 1, 2, 3 minus -4, 0, 5. And this is going to be, again, you don't have to write this out. I am just doing it for completeness, let's say. So this is going to be 1 minus a -4, comma 2 minus 0, comma 3 minus 5. So this is going to be 5, comma 2, comma -2. And that's A minus B. D. Now in D, that's for 2A. 2A. Now this is going to be 2 times 1, 2, 3, which by our definition, and again, don't need to write this out, 2 times 1 plus 2 times 2 plus not plus, comma, 2 times 3. So this is just the vector 2, 4, 6. And again, that would scale the vector. That will stretch the vector to be double its length, and it will actually maintain the same direction. 3 times b. So b is minus 405. Let's jump to that. So this is minus 12, 0, 15. Okay, so I just skipped the step. F, hopefully I didn't lose anybody by doing that. F, 2a minus 3b. Now, 2a minus 3b. Now, you could have used the answers from before, but let's just do this from scratch. It's 2 times 1, 2, 3, minus 3 times minus 405. So this is going to be 2, 4, 6, minus 12, 0, 15. And so that's going to be 14, 4. And 6 minus 15, minus 9. And that's that answer. So again, very natural operations here, especially when you look at the components. Kind of the things, like if you didn't really know about vectors and someone just said, guess how you would combine these, guess how you would add them, guess how you'd multiply this. This is kind of the things that people would guess would work. So it's very natural in that way. Now, not all things with vectors are that natural, just to warn you, but addition and scalar multiplication are that natural. Now, here is another important thing that I want to mention with vectors, is the standard basis vectors. Now, I don't really want to say what those guys are, but that's what they're called, standard basis vectors. And most people, especially if you're in physics and you work in 3 dimensions or 2 dimensions, know these guys as I, J, and K when it comes to the Cartesian coordinate system, the rectangular coordinate system. In more abstract mathematics, we call these guys E sub I. That's notation where the I represents the position that a 1 is in and 0 is everywhere else. So E sub 1 means 1 is in the first position, 0 is everywhere else. E sub 2, 1 is in the second position, 0 is everywhere else, and so on and so forth. And this can go to any dimension. But in R2 and R3, in 2 dimensions, 3 dimensions, the one with the 1 in the x coordinate is called I, the one with the 1 in the j coordinate, in the y coordinate is called j, and the one with the coordinate in the z coordinate is called k. I have them written down here and defined. And so basically, geometrically, these are guys that run along the axes. So if you were to write them as position vectors, they would run along the axes, okay? So the vector I is the vector that goes like that, right? Runs along the x. It stops at the number 1, and this is called the I vector. I don't know if... And then you have another vector that runs along the y-axis, again has length 1. This guy is called the j vector. Then you have another vector that runs along the z, again up to level 1. This guy is called the k vector. Okay, so this is I, J, K. I runs in the X direction, J runs in the Y direction, K runs in the Z direction. And they have components 1, 0, 0, 0, 1, 0, and 0, 0, 1 respectively. Of course, the two-dimensional versions, there is no K, and it's 1, 0 for the I and 0, 1 for the J. Now, what's nice about these guys, and by the way, this is one of the reasons why they're called basis vectors, but really you won't get that. You'd really need to have taken some linear algebra to understand what that is, because basis vectors includes this property that I'm about to mention. Notation wise, we can write any vector in terms of these vectors, which is a part of the reason why they're called basis vectors. We can express any vector in R3 in terms of I, J, and K. This is called the IJK notation. And for example, here's how we would do it. So let's say, suppose we have a vector A where I give it components A1, A2, A3. Okay, then A, which is equal to A1, A2, A3, I can write this actually as A1 times 1, 0, 0 plus A2 times 0, 1, 0 plus A3 times 0, 0, 1. And this line works by vector addition and scalar multiplication as we defined them earlier. But that guy is actually just I, the 0, 1, 0, 0, that's I hat, sometimes you call it I hat, plus A2J or J hat, plus A3K or K hat. And so we can write a vector in that way. So for example, I can have a vector 1, 2, -3. And this can be thought of as I plus 2J minus 3K. And these guys, same thing, just different notation. This guy's the component notation. This guy's the IJK notation. However, I must give you a warning at this point. Do not mix notations. So choose if you want to use IJK or the component notation. Don't do both. So if you have like I, comma, like 2J, comma, minus 3K, that doesn't make any sense. You're not supposed to write that. And similarly, you can't have like the brackets where you have I plus 2J minus 3K and put the brackets. Doesn't make any sense because you're mixing the brackets with the IJK notation. Do not either use the sharp brackets and write it as a with commas, or use IJK and write it as sums of the components. You can't use both. Okay. Now, the last thing I want to mention in this section, see, wasn't such a bad section, right? Is the idea of unit vectors. And again, these guys are super duper important. And we're not going to be able to fully appreciate how important they are in this course, but in the next course, you will start to appreciate just how important these guys are. But a unit vector is just a vector whose length is 1. That's it. A vector whose length is 1 is called a unit vector. That's it. But there are a lot of things that we can describe with unit vectors. There are times when we're going to want to describe a direction, but we're going to want to describe it with a vector that has magnitude 1, because sometimes we're going to need to do operations that involve moving in that direction, and we want to use vectors in order to do the computations necessary for those operations. But at the same time, when I take the vector and put it in my calculations, I don't want this calculations to be scaled or multiplied or become negative or stretched by me using that direction. So just use a vector with magnitude 1. When we plug it into certain situations, it won't scale anything. So it will leave everything in the right size that they should be. Is one way I can do it, tell you why these guys are important. We'll define a lot of things using unit vectors, and just in general, there might be situations where the direction is important, but we don't want the magnitude to mess anything up that we're working with. So unit vectors are going to be important. Now, if you have a vector that you care about, and you know you want to move in that direction, but you don't want to scale anything in that direction, how do you find a unit vector in the direction of that vector? Well, you use this formula that I have here. Simply dividing a vector by its magnitude would force it to have length 1. So, for example, let's say here's a vector, 2, minus 1, 3. If I wanted to find 2 unit vectors in that direction, so what I would do is I would find the magnitude of A, which, as we know, is going to be 2 squared plus, could have done 1 squared, but whatever, minus 1 squared plus 3 squared. So that is radical 14. So this means a unit vector is A over the magnitude of A, in the sense that I can just write this as 2, minus 1, 3 divided by radical of 14. And I could write that as something else, or 2 over radical 14, minus 1 over radical 14, 3 over radical 14. Okay, so I can do this, or this. The other. So this is 1 unit vector. The problem asks for 2. Can you think of, maybe take a second to think about what the other one would be? The other would be the negative. So this is the other unit vector. Just take minus u. So that would be minus 2 over radical 14, positive 1 over radical 14, minus 3 over radical 14. That's the other one. And what does that mean? So here, if I were to like draw an illustration of this, I can have my vector A here. So this is the vector A, and his length is the square root of 14. Now what we just found is a vector u that is running along A, right? So it's the same direction. So this is the vector u, and the length there is 1. So it's just a vector, the same direction, but length 1. And minus u is just going to be the vector in the opposite direction. Now it's along the same line, that is minus u. And this also has length 1. Okay, so A is just some vector. I want to find a vector in that same direction, but has length 1. Or maybe the exact opposite direction. These two, by the way, by our early definition, they are parallel. So in a lot of cases, picking either one is going to work for us. But it just means I want to find a vector in the same direction, say, running along the same line, but its magnitude is 1 as opposed to whatever magnitude of the vector is there. And yeah, that ends this lecture. So yeah, that's basically introducing vectors, what they are, how they work, how they operate. And again, I think a lot of you would remember all this stuff from high school, but I just want to remind you of all the important properties that I'm going to be taking advantage of in our next lecture, the next time I actually see you guys live. So I'm gonna post this. I will post the notes to this as well, so you can just read through it quickly. It should be fine after doing that. And so when we get into the next topic, which is going to be super cool, at least I think, not as cool as the topics I wanted to do at the end of this, but ending with these two, the dot product, which I want to do on Tuesday's class, and the cross product, which I want to do on Wednesday's class. We're going to look at some really cool operations with vectors, because you would notice that I spoke about vectors and I spoke about addition and scalar multiplication, but I didn't talk about multiplying vectors. Is there a way to multiply vectors? Well, in the strictest sense, no. There does not exist a multiplication of vectors like how we can multiply numbers, because there's really no division of vectors. I'll talk a little bit more about that, but let's just say we are going to talk about vector products, quote unquote, but they're not products, because once you actually multiply the vectors, you can't actually like divide it out. So it's not like a real multiplication. It's literally some other meaningful way to combine vectors to get meaningful results. And we'll talk about that next time. It's going to be pretty cool. It's going to be the dot product and the cross product. I will pick up with that on Tuesday. Until then, stay safe. You guys did a mock test today. Hopefully that went well. Maybe I'll talk a little bit more about that on Tuesday. But on Tuesday, we'll start the dot products. It should be fun. And we'll just stop right there. And yeah, I guess that's it. So